Hello everybody, welcome back to this channel. And today we're going to talk about the circuit theorems in S-domain. As always, I'm going to leave the link to the Google Colab notes for this lecture in the comment, in the description down below. And I welcome any comment you may have. Please leave them in the comment area. It's always a good pleasure to have feedback from you. And so today we're going to cover two topics. One is superposition, and the second one is Thevenin and Norton equivalent circuits. And these theorems have been covered in the past, right? In 201 in the resistor network and also in the phasors. So I'm not going to go into details about the theorems themselves. Instead, focus on the examples, and based on the feedback I received from my own class, and you would like to see more detailed math to work into the very end, so I'm gonna spend a little bit longer time on the examples. So today probably we're gonna have 3 video clips. Each video clip may be a little bit longer than usual. I hope you will enjoy it. And let's start with the superposition. And the superposition, remember, if we have multiple sources, and each time we can solve for the partial solution by having one of the sources on only. That means we turn off all the other sources. When the voltage source is turned off, that means the voltage across that element becomes 0, and the current could be anything that's exactly identical to a short circuit, right? And when we turn off a current source, that means the current through that element will be 0, and the voltage could be anything that's equivalent to an open circuit. And this is different from we're shorting the voltage source. We're not shorting the voltage source. I think I got the question from students saying, do we, in the practical world, do we short circuit the voltage source? No, we don't. Not even in the academic world either. So if we're replacing that voltage source by a short circuit, and we're replacing the current source by a open circuit when we turn them off. Okay, when we turn them off, that means we don't want them, and it's different from remove them, because remove them means you leave them open. So I hope this will clear the concept. It's very critical you know this, because otherwise you may start with the wrong circuit. Of course, you're gonna get the wrong answer, right? So let's look at the first example here. I have a very simple RC circuit, and this RC circuit is supplied by a step voltage source. And let's see the VA, these are known. VA, the R, the resistance value, these are all known values, right? And also we also know the V sub C0, these are all knowns. And we are trying to find the V sub CT, and we're trying to identify the zero state response and zero input response. Remember what the zero state response? Zero state means the zero initial condition, right? So zero state response means the response due to the input voltage only, and zero input, the zero input response. This is quite informative, right? So in this case, and due to the initial condition only, because zero input, due to initial so let's see if we can identify this in the S domain. So we don't like solving different equations, right? So we transform this circuit into S domain. First, the voltage source, we take the Laplace transform of that step function, that becomes the VA over S, right? And then we have the resistance, the impedance in the S domain for resistance the same. And we have the capacitance. Capacitance will become an impedance in series with a voltage source. And you could use impedance with in parallel impedance in parallel with a current source. But in this case, this will be slightly easier to solve. Not that much, but it's slightly easier to solve. So in this case, this voltage source here should be equal to VC0 over S, and the impedance for the capacitance is 1 over CS. Right? The voltage across this capacitance, the corresponds to V sub CT is V sub CS. V sub CS. Remember here, this is the V sub S, including this initial condition. Make sure you don't just put a V sub CS across this impedance. That would be wrong, right? If you just put it across the impedance of the 1 over CS, that would be wrong. So in this case, we're gonna have the zero state response. Let's say the zero state response is due to input only. That means we would like to have, so we can use superposition. So let's see, we're trying to find a zero state response first. And the zero state response is due to input only. So in this case, I redraw the circuit. And I have impedance here. And in this case, I have a short circuit here. I turn off this source here. And in this case, I have V sub A over S. I have R 1 over CS. And so this is the V sub C. Let's call zero state V sub ZS S. Okay, capital V. In this case, I can find the voltage across this one. This is not too difficult to find, right? The most straightforward way would be the voltage division, right? We just talked about this last time. In this case, the voltage division for V sub Z S is zero state. This subscript here, subscript ZS stands for zero state, and that should be equal to the voltage, the impedance 1 over CS, and R plus the sum of these two impedances, and times VA over S. And in this case, let's see if we can work out this so let's see if we can get the better form of this. What I do is I multiply this by S and divide it by R. So I do the same thing for the denominator also. In this case, what I get in the denominator here is, so on the numerator first, so I get a 1 over RC, right? On the denominator here, I get the first term, I get a S plus, and second term here, I get a 1 over RC as well, and times the VA over S. And now I can do the partial fraction expansion, right? So I can do the VA, or let's see, K over K1 over S plus K2 over S plus 1 over RC. And we can identify when this has two poles, right? One pole is at 0, S equal to 0, and the other pole is at S equal negative 1 over RC. Remember what the RC is? RC is a time constant for the first order circuits, right? And so, and we can find the K1 and the K2, the residues, by using K1 is equal S times V sub ZS S. That's equal to, let's see, 1 over RC. But in this case, and we value the S as 0 at this pole here, and we have a 1 over RC S plus 1 over RC times VA, and S being cancelled, right? So in this case, S equals 0. What do we get? We get a VA, and based on some residues, we know that K2 should be equal to minus K1, right? Because K1 plus K2 should be equal to 0, because the order of the numerator is 0 and the order of denominator is 2. So let's see if that's the case. In case we made a mistake, we can find out. So in this case, you find the K2, I multiply S plus 1 over RC and Z V sub ZS S, and now we evaluate this at this pole, which is negative 1 over RC. And in this case, so this denominator being cancelled, I have negative 1 over RC times VA over S, and S equal negative 1 over RC, and therefore this equal negative VA. So no surprise there. So therefore the V sub ZS S is equal VA over S minus VA over S plus 1 over RC. And if we do an inverse Laplace transform, so V sub Z, so the zero state response in time domain is V sub, using lowercase v sub ZS T is equal to inverse Laplace transform V capital V ZS S. And this one here is, the first one is UT, right? So VA times UT. And the second one here is, so the first one here is UT, and second one also has UT there. But this one here minus E2 minus 1 over R, so T over RC, right? So that's the, and let's see if this makes sense. Hopefully it does. So yeah, T equal to 0, that means this is 0, right? So because this is zero state response to the capacitor voltage. So this is part of the solution, right? This is not a total capacitor voltage. And at T equal to infinity, the capacitor voltage is going to be equal VA, which kind of makes sense, right? And let's find the zero input response. So zero input response in that case, so that we need to turn off the input source. So we will replace that by a zero by short circuit and draw the rest of the circuit. And for second one is the zero input response. So in this case, we have the RC. So we have this, draw the rest of the circuit, V sub C 0 over S and 1 over CS. We still have the V sub, so in this case, this V sub CS, we call the zero input, we call ZI. ZI, using capital M probably. Did I use, yeah, I used capital. So let's call ZI zero input S. And now I replace the input source. Since I turned it off, I'm replacing it with a short circuit. I did not short circuit that voltage source. Okay, I just remove that. I replace that by a short circuit. So in this case, the voltage across. So by the way, the V sub ZI is just the voltage across this resistance, right? So now we can again here apply what we call the voltage division. So in this case, let me write down here. So in this case, V sub ZI, zero input, that's going to be equal to R over R plus 1 over CS, right? The impedance, so the voltage across R times the total voltage, which is V sub C 0 over S, right? So in this case, let's see if I can divide R on both numerator and denominator. So the first thing here, I divide R and I divide R. So in this case, I got 1 over 1 plus 1 over R C times S. And since I have V sub C lowercase, because this initial condition v sub c0 over s. So I multiply the s on the denominator. I get s plus 1 over rc, and on numerator still 1. So I put the v sub c0 there. And this one is the inverse Laplace transform is very easy, right? So the input response in time domain is the v sub z I t is the inverse Laplace transform of v sub z I s. And in this case, that would be equal v sub c0 times e2 minus t over rc and times ut. And so in this case, the voltage, so the voltage at t equal to 0 is equal to the initial condition v sub c0, right? And at t equal infinity, this term will become 0. So this initial, without the input, this will decay to 0 exponentially. So that's the 0 input response. And I will do another example on superposition. It's a more complicated one. I had that one in the Google Colab notes, but I did not solve by hand. I solved using Python. But I'm going to illustrate how to solve that problem by hand.